Okay, thank you very much again. So in the second lecture, we are going to first talk a little bit more about the linear maximum principle, because we need the boundary version. And then we are going to generalize to any, let's say, any elliptic operator. Let me talk a little bit about the boundary case. So boundary of maximum principle. Okay, we need some definition in order to state it. We are not going to prove it. We are just we are just going to state it. We get a function u defined on a domain omega. As usual, omega is a domain in Rn. And we take a differential operator of second order, as usual, L, uniformly elliptic. Linear. And we assume, let's say we assume that L of u is larger or equal than 0, and L that is of the form AJ UE, well, let's write it like that, B square U dxi dxj plus bi du dxi. Here, I don't put the sum, but it's sum over ej, sum over I. And we assume, as usual, that AJ and BI are bounded. I mean, I'm going to be a little bit sloppy with the assumption. We already did them in the last time. Okay, so we already know that U cannot have an interior maximum. So now, in order to take care of the boundary of a boundary maximum, we have to define what is the exterior derivative, what is an exterior derivative. So we let n be the eta 1 nu 1 nu n, the exterior normal to the boundary, exterior normal to the boundary of omega. So you have omega here, and you have an exterior boundary normal at a certain point P. So we say that it's very easy, but we have to define it. We say that nu is an exterior direction. An exterior direction if, of course, if the scalar product n times nu is larger than 0. So you have, did I call it nu? Yeah. Okay. So you have n here, and nu like that. Okay. We also say that nu point outwards if you want. So the exterior derivative with respect in the direction, let's say in the direction nu is called the nu, of course, and is defined as the limit for x going to P point x of omega going to p, of the scalar product of nu times grad u of x. Okay, that is also, of course, the limit for x going to p of sum over I of nu I du dx. Okay, this is just a definition. Okay, if u happens to have a maximum at the boundary like that, then one knows that all these derivatives are larger or equal than 0 at that point. Okay, because it has a maximum there, so they should be. What Hopf proved is that the strict inequality hold. So the theorem is the following. Okay, so L is like that. Assume L, U, in the assumption before, is larger or equal than 0. And all the assumption. Above. And that let U smaller or equal than M in omega, and U of E equal to M or at some point P of the boundary. And then here we have to do a further assumption about the boundary of omega. We have to assume that P belongs to the boundary of a ball contained in omega tangent at the point. So it belongs to a ball contained in omega. It's sufficient to say like that. I mean, you need that P belongs to is a point like that. It cannot be something like, okay, like that. This is the interior ball condition. It's known as the interior ball condition. And I mean, we are not going to give the proof, but you remember that we did the proof for the interior point. We have to take balls around the points. So we need that the function is defined in a neighborhood of, not really a neighborhood because it's a ball, but we need a ball inside. If you think a little bit about the proof, yeah. I mean, you need, in fact, that, okay, the boundary of omega, you don't need, I mean, you only need regularity around P, around the maximum point. If not, you can take continuous, okay? And you only need that the function, in fact, I didn't say it maybe, yeah, I will say it in a moment. U has to be continuous to the boundary, has to be differentiable only at the point P. You don't need more regularity. Okay, so if U, here it is, if U is continuous in omega union boundary of omega, and this derivative exists in P, for all exterior direction. In fact, no, not for all. Exists in P for the exterior direction. It's less. Huh? No. Then this derivative must be positive. You don't need more than this. Okay? Okay, so we're not going to prove it, but it's really very similar to the interior case. And I would like to add that a boundary maximum principle also hold in the case where you have this h less or equal than 0. Okay, you remember that at the end of the class last time, we extend the maximum principle to the case where the interior maximum principle to the case where you have to add this. This was like L of u plus HU larger or equal than 0 with H smaller or equal than 0. Then also in this case, you cannot have a boundary maximum principle that is not negative. Okay, so everything holds. Okay, just a remark now about the, here omega can be bounded or not, but the consequences are a little bit different. The consequences of the maximum principle are different if omega is bounded or not. So for example, just to point out something very simple, but okay, it's not really a remark. Okay, if omega is bounded, you can use this maximum principle to, for example, to prove that the value that two function, if there is an inequality for two functions at the boundary, then this inequality is you have this inequality also in the interior of omega, and that's very simple. For example, if you have L of u larger or equal than 0 and L of v equal to 0 in omega, and then you have u smaller or equal than v in the boundary of omega, okay, then it's easy to see that u is smaller or equal than v in omega. And this is very simple because you take proof. It's a classic, right? You take v equal to w, sorry, equal u minus v, and then so you have that w at the boundary is 0. So L of w is equal to L of u minus L of v, so it's larger or equal than 0. So it cannot have an interior maximum. So W does not have.
Sorry, Barbara. Am I misreading? So you said W is less than or equal to B on the boundary. How do you get that W restricted to the boundary 0? Oh, wait.
U is less or equal to V in the boundary.
And then you define.
And I want to prove that it is the same holds in the interior.
Right, but then. Yeah, that's fine.
Yeah. Sorry.
No, that's fine.
Yeah. You're right. I'm sorry. Thank you. So W cannot have an interior maximum because of the maximum principle. Does not have an interior maximum. So the maximum must be at the boundary because it's a omega bar is a compact set. We have omega bounded. So interior. So W as maximum at the boundary. Boundary. So W is smaller or equal than 0 in omega. And that means that U is smaller or equal than V in omega. But if omega is unbounded, of course, you cannot assume that W will have a maximum. And so you have examples that contradict this. For example, you can take omega as a very simple example as a strip xy in R2 such that y is in 0 pi. So it's just this strip, and then you take u xy equal to e to the power x sinus y. Okay, you can see that this is harmonic. So, and u is 0 at the boundary. But clearly there is no maximum. Okay? It goes to infinity. So, okay, this is just to talk a little bit about the boundary case. Okay, so now we are going to prove a maximum principle for a general elliptic operator. That is the one that we are going to use most of the time, not every time, but okay. First, we need to prove a little extension of our maximum principle, the linear one, the one with the L plus H. Okay, we need a little extension that, in some cases, make us free of taking H negative or non-positive. Okay, so it's a little bit tricky, but it's very useful. So first, let's call it a proposition. And so you take, again, omega in Rn. Let me take now, here you can take, let's take it very regular because we don't know where to go exactly. So it's a more general factor, so we don't know. Let me take, I can take it C2, but I can take it also smooth. Doesn't matter. It's really, you can choose your favorite regularity, provided there is some regularity, the necessary regularity. And then you take your operator, linear, that is Aij du d square u d xi dxj plus bi du xi plus c u. C is not a constant, is sorry, hu. H any sign, and then this usual assumption on L, regular, bounded, uniformly elliptic, and so on. So now assume that L of u is larger or equal than 0, u smaller or equal than 0 in omega, and there exists x0 in omega such that u of x0 is equal to 0. Then u is identically 0. So you see, this is a general maximum principle only in the case where u is strictly negative with any h. Okay? But only in this case, it's very important, the sign of u. Why? Let's see the proof. It's very simple proof. I was a little bit surprised when I saw this for the first time, but it is true. Because, of course, in general, it isn't. But if you have this sign on u, it works. So the proof is like that. It's a trick. Let's say we write L of u like as L0 of u plus h of h times u. So we take this is the not really the principal part, the part with the derivative. The principal part usually is the second derivative part. And define, I always have to think a little bit about that to prove it. Define Q of X equal to the minimum between H and 0. H of X, H of X, and 0. Then what you have is that Q of X minus H of X is negative, is non-positive in omega, by definition. Okay, so now consider L0 of U and L0 of U plus Q times U. Okay, this one you can write, recall that Q is negative now, is not positive now. So this one you can write like L of U minus H U plus U. So it is L of U plus Q minus C U. Minus H. I have C on my paper, so I'm confused about that. And this is negative. So here you can apply the maximum principle you know. So now, it's easy. So this is larger or equal than 0. Okay, because this we know that is positive, this is negative, and this is negative as well. So this we know that is larger or equal than 0. So by the maximum principle, apply to L0 plus Q, where Q is negative, is non-positive, you cannot have an interior maximum. So in this case, as U was, there is no point, interior point where U is 0. Okay, so it's a maximum principle even in the case where H is not the good sign. Okay, so let us use it. Okay. We are going to define a general elliptic operator. So it's something like that, is a Q of U equal to a function of X, U, gradient U, Hn of U. And of course, the domain here is omega times R times Rn. This is a symmetric matrix, so it's R. Okay, so this is the domain of definition in general. And we assume that we call this variable X, this variable Z, this variable P, and this variable S. So assume that F is a differentiable with continuous derivatives, at least. Continuous derivatives in all variables. So assume that this matrix is positive definite. Okay, this means that this is the notion of ellipticity. So then F is elliptic. If you think about the quasi-linear case, are just the coefficient of the ij, yeah? If you, because I didn't tell you maybe that, I mean, F can be something like Q of U can be something like sum aej x u gradient u, d square u, dxc, dxj. In this case, the operator is called quasi-linear because it's linear in the second derivative, and this is the minimal surface case or the constant mean curvature case. We wrote the equation in the first class. Okay, so this is more general definition. And of course, when you do the derivative with respect to this variable, you have the matrix A. So it's the ellipticity. Okay, now theorem. Let U and V from omega to R such that F, let me write it just, no, I write like that. Fx U gradient U Asian of U is larger or equal than F X V gradient V Asian of V in the domain, let me say. Moreover, if U is less than or equal than V in omega, and there is a point where they coincide in omega, then U is equal to V in omega. Okay, this is the maximum principle. One call it also the tangency principle for a reason that will be clear in a moment. Okay, here you have to assume, you will see, you will see. I'm a little bit sloppy with the assumption again, but you will see what you need in a moment. Proof. Proof is very simple. We are going to use this proposition that I'm cleaning, but in fact the main tool is the mean value theorem. So proof. We have to write, so mean value theorem. The mean value theorem helps to write the difference, this difference f of u minus f of v as a linear equation. So let's write like that. 0 smaller or equal than f x v gradient v Asian of v. It's a computation now, so let me be a little bit annoying, but the u, okay, this is the assumption, larger or equal than 0. Now we are going to write this difference as a sum of 3 differences. So it's equal to f x u gradient u Asian of v minus, let me write and then I will do some comment, x u gradient u Asian of u plus f, all here you have 3 different entries. Now each of the lines will have only 1 different entry so that you can apply the mean value theorem. So if fx U gradient V Hn of V minus F, this one, X U gradient U Hn of V. And then the last one plus X F X V gradient V Hn of V minus F X U gradient V Hn of V. Okay, you see that these two are equal, these two are equal, so it's fine. It's the right inequality. Okay, we apply now the mean value theorem to each line. We can do it, yeah, because it's here you have just this as a different entry. Here you have the gradient, and here you have the function. So apply mean value theorem to each line. Okay, so set, I need to write something, set alpha ej is the derivative of f in the variable Sej computed at the point like that, xu, gradient u, and theta 1 Hn of v plus 1 minus theta 1 Hn of u. And beta I is the derivative with respect to, was p, yeah? Pi of f x u, and here theta 2 gradient v plus 1 minus theta 2 gradient u. And here you have, yeah, Hn of v. And then C is equal to d dz. Z was the variable, the real variable representing u. F of x theta 3 v plus 1 minus theta 3 u gradient v Hn of v. Where, of course, theta I are a function of x taking values in 0, 1 is the convex combination. Yeah, so function of x in, let's say, 0, 1. Okay, so these are suitably chosen. And then you can write this inequality by the mean value theorem, because these are the functions coming out of the mean value theorem. You can write it like sum over ij of alpha ij times v minus u ij plus sum over I of beta I times v minus u derived with respect to I plus c v minus u. Okay, so it's a linear equation in, let's say, W. So if you write, W equal to V minus U, you have 0 less than or equal to alpha Ej, W Ej plus beta I, Wi plus, what do they call it, CW. And it's a linear PDE with W larger or equal than 0 by assumption, and W like 0 equal to 0 at a point because of our assumption there. And this means that W is identically 0. And here we are using the fact that we don't need a sign for C, as I told you before, the previous proposition. We don't have a sign for C, but we don't need it because of our choices, because you have W larger or equal than 0. Okay, so Did I write it correctly, or it's the other way around? Wait a minute, because this is a minimum. Huh? I maybe did a mistake of, I wrote it with the wrong sign, probably. How was my assumption? Let me see the assumption, because I'm not sure about that. This was positive. Yeah, you have the other way around, yeah. It's just changing the sign here, yeah? Okay, now it works. Okay, yeah, so it's correct. Okay, so now, let me see, what time is it? Okay, so now we are done with the maximum principle. You know, this is you can call it a tangency principle, because if you remember what we say at the beginning of the course, it was something like you have two surfaces, tangent or hypersurface or whatever, tangent at a point P that satisfies the same or not really the same, because you just need an inequality between the equation that you have. You F in one of them smaller or equal than F, this big F in the other one. So if the one is a large, let's say that this is V and this is U. So if one is larger than the other and they coincide at a point, then they coincide everywhere. Okay, this is the meaning of what we wrote here. So there is no boundary involved, it's just an interior maximum principle, or tangency principle, as we can call that. And as I told you, if you have a CMC surface, you can write it as a graph locally above the tangent plane, and the graph will satisfy a quasi-linear elliptic equation, in fact, so it's simpler than this. So in fact, this maximum principle holds for much more in general. And then magically, if they touch at a point, they have to coincide, okay? Because they satisfy that. Okay, now we can prove with it. Let me just make a toy application, but that I find very nice. Sorry? In the parabolic. I think that, I mean, for the linear, yeah, I think so. I think so. It's in the book by Protter and Weinberg, the linear case. But I don't know the details about that. Okay, so for the linear case, Protter and Weinberg book is the one that one has to look at. For this more general case, I was talking with Jason and I was looking for the proof, for a book where you can find the proof. And in fact, I didn't find it. There is the proof that one has in the last chapter of Gilbert-Rudinger, that is a book of partial differential equation, in fact, quasi-linear for all the book, 16 chapters, but then the last chapter is about fully nonlinear, but it doesn't give this proof. It gives the proof for the case with H smaller or equal than 0. So, yeah. Yost. Yeah, probably. So I remember that I saw it somewhere. I mean, it's not out of my mind. I knew that it was true. Then I saw it somewhere. So maybe the book of Yost is the right one. Because I was looking this Sarrin-Pucci-Sarrin. There is not this maximum principle. So maybe, yeah. So let's give a look to Yost book. Thank you for the suggestion. Okay, so as I told, let us do a toy application. So first, we agree on the fact that a CMC surface, CMC-H surface, or hypersurface, it's, let's talk about surface. It's the same, but it's easier to write surface. Satisfy quasi-linear elliptic PDE. So one has the maximum principle. One has the maximum principle. I call it the maximum principle. I mean the last one that we proved. Okay, so exercise. There is no CMC entire graph on R2. So entire, I mean on complete on R2. Okay, so CMC H different from 0. Okay, why? Okay, now this one we are going to prove very quickly. Okay, just a remark. If H is equal to 0, this is a big theorem. This is known as Bernstein theorem. So there is no entire minimal graph on R2. It's very well known. And one should say that Bernstein theorem is true even in higher dimension, but only till dimension 7 or 8. It depends if you look at the ambient space or Rn. Because then there are the famous counterexamples by Bombieri, De Giorgi, and Giusti that found out entire minimal graph in higher dimension. Okay, so but it's a theorem. I mean, even in the case n equal 2, you need a proof. I mean, it's you have to use isothermal parameters and the Weierstrass representation. I mean, it's not Weierstrass representation, no. It depends. There are different proofs. You can use different proof of that. But it's really a theorem. Okay, this is true in any dimension, and it's very easy to prove. So let's try to, some students should try to tell me something. Proof. Remember that we have to use the fact that two CMC surfaces with the same mean curvature cannot be like that. Cannot be tangent at the point with one on one side of the other. So the assumption here is that, proof of this, is that we have, let me take some more place here. Yeah.
Sorry, but it's, I was just, when you say exercise, there's no CMC, not zero graph over R2, that's correct. And then you say...
There is no CMC, no zero entire graph. There is no, it's correct.
You know, some people might think there's the plane, but the plane is not constant mean curvature.
The plane is a zero mean curvature.
Exactly, and then look at your next line. There is no, other than the plane.
Ah, yeah. Sorry. You're right.
Yes, that you have to remove the plane.
No, it's very important.
It gives a sort of...
Yeah, right. Other than, I'm sorry. Then the plane. Yes, of course. Exactly. The plane is the only exception to Bernstein theorem. Another way, the only minimal entire graph is the plane in R2. The only minimal entire graph. Minimal, I told minimal, yeah. Sometimes you forget fundamental assumption. Okay, so now in the case of TMC, you have a graph, or you can go also I mean, it's a graph entire. So, okay, let's go a little bit further. It has constant mean curvature. So constant mean curvature means that the mean curvature vector that I didn't define, but it's, I mean, H is the mean curvature vector. That is, if you choose a normal, you can write it like as the mean curvature times the normal. So as H is constant, once you choose N, then the mean curvature vector point up or down. Okay, it depends on the sign of the curvature. But anyway, we can think that it is pointing up like that. And that's constant norm. So, may you do something with that? Let us, we have to make the comparison between this and another surface. So we have to look for another surface that we know very well. He's saying the plane, but the plane, it's a very complicated stuff because you have first to find the plane, you have to guarantee the fact that the two surfaces touch at one point and they are only one side of that. So for example, here, okay, assume that my picture is something like that. Okay, that go up like that and down like that. So any plane intersects the surface. It's bad. So you need something that is not non-compact. Look for something compact. The sphere, very good. So let's take a sphere of the same mean curvature of this, and let's put it above the surface because we choose this vector. So a sphere here with constant mean curvature h, the same. And of course, as the sphere is compact, we can guarantee that we can put it in a position that doesn't touch the surface. Okay, it's above, really above. And now do a vertical translation and get the first time that they touch. It's here. So it's the first time, so they're tangent. Their mean curvature vector are equal, contradiction. They should coincide, but one is compact and the other one is not. Okay, so very easy. Very easy, but very nice result. And this is a really, let's say, a toy application of the maximum principle. Okay, so let me see. Yeah, of course. Yeah, you need graph, because otherwise not true. You use graph exactly for this, because you have to guarantee that you have a sphere, disjoint, and you're not sure about that in general, of the same mean curvature. Of course, you can always find the, let me just say something else. Why, for example, if you take two spheres of the same mean curvature, yeah, you can put that, it's very elementary stuff, but one has to think about that. Same radius, same mean curvature, tangent at a point. Why this is not a contradiction? Yeah, I know that you know. Franz knows. Why this is not a contradiction? Yeah, exactly, because the mean curvatures are not equal. Yeah, because you have to choose a normal. So let's choose this a normal to make the computation. So this sphere has curvature, let's say 1 over r with respect to this, but this one has curvature minus 1 over r. And so you cannot use the maximum. This is important because, okay, so let me see what I can say more in this 10 minutes. Okay. Okay. I will not finish, but I want to start. Another very nice application of the maximum principle. Here, we are going to do an application of the linear maximum principle, of the maximum principle in the linear case. But it's related to CMC surface. So let me announce, and then we will do the computation next time. Height estimates. For CMC H different from 0 graphs. I'm too bad because I'm doing everything for CMC different from 0, not minimal. So it's, but I will try to do something minimal as well. Okay, so this is the statement. Goes as follows. Okay, you take a function u, defined on omega, that is a subset of R2, a domain and a compact domain, bounded. And so you assume that the graph of u has constant mean curvature. H. Then I want to say as a height estimate. So the maximal distance or the maximal, I don't know, distance between, okay, I forgot to say that u restricted to the boundary is this 0. So it's exactly like that. I mean, it's a graph with 0 boundary value. Okay, it touched the plane here at the boundary. So the maximal distance between, I like best to say the maximal height. I don't know if it is correct in English, but the height of the graph of u with respect to the plane x3 equals 0 is smaller or equal than 1 over the absolute value of h. You can think h positive if you want. The sign of h depends on your choice of the normal vector. Okay, so that's very interesting because it doesn't matter which is the domain. It can be a huge domain. But anyway, you cannot be too high. This is sharp for the sphere, exactly. So think about that. If you take the sphere, this is exactly 1 over h here, the half sphere. But, okay, for example, it's very easy to prove this theorem if your domain, for example, is contained in this ball, in this disk. Then it's very easy because you come from the height with the sphere. You have a first touch point if you have a height higher than 1 over h. But this is very simple, just the maximum principle. But here, you cannot do that, yeah, because here, of course, you can find a sphere, very big one that let's say, when you go down, it contains the intersection with the plane contains the domain omega. But that sphere will be, in general, can be very big. So its mean curvature will be small. And so a small mean curvature, I mean, if I put here, let's see, if I put here a plane, there is no problem. I mean, this curvature is less than this curvature. So you have no contradiction. You don't have the right inequality between the two equations. Okay, so this you can always do. And so you can also put a very, very big sphere. it's not useful. So here you need something else. And who did this something else was Serring. And he used, in fact, how much time do I have? It's finished? 5 minutes? Okay. Okay, so Serring proved this theorem. They are known as Serring height estimate. Serring was a great guy. He proved many things about CMC, about PDE, in fact. Was a PDE man, but he knows very well the geometry, so. Okay, and what he used in fact the Laplace-Beltrami operator on the surface. Let's say the surface here, it's more general. If you, I want to say just one more thing. There is a generalization of this theorem that goes as follows. I will not prove it, but I want to say the generalization. Maybe it's. If you have M is a CMCH larger than 0. Just one thing before. Here you need really H larger than 0 because it's 1 over H. If you don't have, for a minimal surface, this gives nothing. Well, first of all, you have something more interesting in the case of minimal surface. If you have a minimal graph with 0 boundary value, it's very easy to prove that it is the plane. Because suppose that this is minimal, then you do what we did before, where you come from, if it is like that, you come from far away with a plane, you arrive to a first point, and they should coincide. But this is not possible till this plane is not this plane. Okay, so of course, any graph with 0 boundary, minimal graph with 0 boundary value is the plane. Okay, so M, CMC, boundary of M contained in the plane x3 equals 0. Let's say bounded. Okay, then the maximal, embedded. No? I didn't need embedded here because it's a graph, but here it's not a graph. Huh? So the maximal height of M with respect to x3 equal to 0 is 2 over the module of H. In the higher dimensional case, you have N here. Anyway, no. I'm telling something completely wrong. It's 2 all the time. Sorry, it's 2. Why is 2? Because what you prove, and that I will not prove this, but you will have an example of the method with which one proves this thing in another case. You prove it using what is called Alexander reflection method, that in fact, if you have a situation like this, so something like, I don't know, this is M, CMCH. What you are able to prove is that you take the maximal height and then you go to the half of it. So this is H and this is H over 2. So you can prove that between H and H over 2, M is a graph. Okay, you can prove it. Yeah, it's not, you can prove it. Not with, using the maximum principle in some sense, but not directly. So you can prove that it is a graph for this first half. So this is, the height is less than or equal than 1 over H. So the double, so you have this, because the height of the graph is H over 2. So then this implies that the complete A is like that. Okay? So it's more general than serving stuff. And here, these I'm not going to prove, but it's really, once I finish, you will be able to prove it as well. Okay, I think I'm stopping here, and I will talk about serving next time.
Do we have any questions?
Sorry?
The boundary of this here, boundary M. Oh, sorry. Should be contained in the plane. So if I put a sphere on top, just touching the plane, would that be allowed in your theorem?
The sphere.
Because the sphere touches the point.
Yeah,
the point is a boundary point.
Yeah, but it's 2h, 2 over h.
That's what I mean. It's
it's sharp. Again.
That was my, so you get sharpness.
Yeah, right. Yeah, you don't need the, it's a degenerate case, but it's, yeah, he's right. He's telling that if you put, it's an interesting, I mean, if you put this, let me do a big sphere, okay? The sphere show you that this is sharp, again. And it's very natural that this is sharp because you are cutting by 2. So it's,
Any other questions?
I cannot listen to you.
Hi, ma'am. Could you repeat the h over 2 less than 1 by?
This case,
Yes,
this
that
last case,
argument
yeah.
again, yes.
So I told that what you are able to prove is that if you cut by 2 the maximal 8, so this is the maximal 8, h, small h that you don't know. Let's call it D. D is maybe easier, it's not small h. So this is the maximal height. Now, cut it by 2, okay, D over 2. What you can prove, but I didn't prove it, is that this first part of the surface is not like that, but it is a graph. Okay? So now, for the graph, you have a Serrin estimate. So you know, and the graph, of course, has height D over 2, because we cut by 2. So you have that D over 2 is smaller or equal than 1 over the absolute value of h. And then the maximal 8 is smaller or equal than 2 divided by the maximum value of h. That is exactly the theorem. Okay?
Any other questions? So let's thank